Previously, we have been introduced to a kind of matrix called the Homogeneous transformation matrix, which allows us to calculate the location of the end effector of the robot manipulator for any values of the joint variables. We learned that a homogeneous transformation matrix has two parts, a rotation matrix and a displacement vector. We learned about rotation matrices in the last set of videos. Today we will learn how to write displacement vectors. First, let's review what a vector is. A vector is generally defined as a quantity that has both magnitude and direction. A typical way to express a vector is by writing out the vector's components. For example, if we are writing a vector in 2 dimensions, we would write a vector with 2 elements. The first element is the x value, and the second element would be the y value. We can use this approach to write the displacement between 2 points. Suppose that we say that the first point is at x equals 0, y equals 0. And suppose that we have a second point that is at x equals 5 and y equals 8. Then we could write the displacement from the first point to the second point as a vector, and we would say that that vector is 5, 8. And we would express that vector as shown here by writing a 5 in the first position and an 8 in the second position. Can you see how this expression has both magnitude and direction? We can see this more clearly if we picture this vector as a triangle, like this. Now, the direction of this vector is defined by the angle here. And the magnitude of this vector is defined by the length of this hypotenuse. Now, we could write the x and y positions of this vector differently. The x position could be written as the hypotenuse times the cosine of the angle theta. And the y element could be written as the hypotenuse times the sine of the angle theta. Now, here is where we can start to see how a vector is really useful for us to define the displacement between one frame and the next frame in a kinematic diagram. In our kinematic diagram, this angle here will turn out to be the joint angle of one of our robot's joints. And the length of this hypotenuse will turn out to be the length of the link. You'll see how this is more when I show you some examples. For my first example, I'm going to show you a spherical manipulator. I also need to draw in all of the parts of this kinematic diagram. I need to label all of the coordinate frames. And I need to draw in my joint variables. and I need to label all of the links. Now, when I find the displacement vectors, I have to find one displacement vector for each set of adjacent frames, just like we did with the rotation matrices. So I should find the displacement from frame 0 to frame 1. I need to find the displacement from frame 1 to frame 2. And I need to find the displacement from frame 2 to frame 3. Each of these displacement vectors is going to have 3 elements because we're working in 3-dimensional space. Now, let's find each one of these vectors one at a time. The displacement from frame 0 to frame 1 means what is the displacement from the center point of frame 0 to the center point of frame 1 expressed in frame 0. I need to have an x value, a y value, and a z value. And the values or the variables that I put into this vector have to be true no matter what values we set for the joint variables. Finding the displacement from frame 0 to frame 1 is fairly easy. The displacement is right here. No matter what value we set for theta 1, theta 2, or d3, the displacement between the center of frame 0 and the center of frame 1 is always entirely in the z0 direction. There is no displacement between these two frames in either the x0 direction or the y0 direction. That means that my x and y values for this displacement will both be 0. What value would I fill in for the z displacement? Here I have to fill in the distance between these two frames in the z direction. And here that value is the link length, A1. Since we're done with the displacement from frame 0 to frame 1, let's go on to find the displacement from frame 1 to frame 2. Once again, this displacement will have to have 3 elements because this is in 3-dimensional space. We need to express the displacement from the center of frame 1 to the center of frame 2 in the one frame. And this has to be correct no matter what values I set for theta 1, theta 2, and d3. Finding this displacement vector is a little more tricky than the first one. Right now, it appears that the displacement from frame 1 to frame 2 is a distance of A2 in the x1 direction. But it turns out that this is not correct. The reason why this is not correct is because this will not be true when theta 2 becomes a value other than 0. Suppose that theta 2 was a value of 90 degrees. If theta 2 was 90 degrees, then our manipulator would not look as it's drawn here. In that case, this link A2 would be going straight up in the y direction and ending in the joint up here. I can't write the displacement as being A2 in the x direction because that won't be true when theta 2 is not 0. Instead, I have to use the triangle relationship that we saw a moment ago. When theta 2 is some non-zero value, the center of frame 2 will be up here somewhere. And frame 2 will look like this. This will be Z2, and Y2 will be pointing like that. And X2 will still be into the page like this. In this case, the link will be going up like this. This distance will still be A2. But what will be the displacement in the X direction and the displacement in the Y direction? The displacement in the X direction will be equal to the hypotenuse of the triangle, which is A2, times the cosine of whatever value theta 2 has. Similarly, the y displacement will be equal to the hypotenuse, A2, times the sine of theta 2. No matter what value we set for theta 2, there will never be any displacement between these two frames in the z direction, which is into and out of the page. So that value will be 0. Now we're finished with the displacement vector from frame 1 to frame 2. Let's find the displacement vector from frame 2 to frame 3. The displacement from frame 2 to frame 3 is right here. Right now, the displacement between frame 2 and frame 3 is entirely in the z direction, that is, the z2 direction. Will that be true no matter what value we have for the joint variable d3? It will be true no matter what the value is for d3. When d3 becomes non-zero, frame 3 will slide to the right entirely in the z2 direction. No matter what value we set for d3, there will never be any displacement between these two frames in the x direction or in the y direction. So for this displacement vector, we can fill in 0 for the x and the y values. Now what value should we set for the z direction? We always draw a kinematic diagram to show what the manipulator looks like when all of the joint variables are 0. So in this diagram, d3 is set to a value of 0. Right now, the displacement between these two frames in the z direction is equal to the link length, A3. But as soon as d3 becomes non-zero, frame 3 will slide along the x direction and the distance between these frames will increase. So the actual displacement between these frames in the z direction is equal to the link length, A3, plus however much the joint variable d3 has moved. So when d3 is equal to 0, the z direction displacement between these frames is just equal to A3. But as soon as d3 begins to extend and the frame 3 slides in the z direction, the z displacement between these two frames becomes bigger. We've now found one displacement vector for each pair of adjacent frames, so we're done with the displacement vectors for this manipulator. Let's take a look at another example. Do you recognize this standard form of manipulator? This is a scalar manipulator. Before I can start to find the displacement vectors, I need to start by filling in everything I need in this kinematic diagram, starting with the coordinate frames. I'll put the z direction as the axis of rotation for each of my revolute joints. and I'll fill in x and y so that they follow the right-hand rule. Z for a prismatic joint is the direction of motion. And once again, I fill in x and y so that they follow the right-hand rule. The end effector frame just copies the frame before it. Next, I have to label the positive direction of the joint variables. For this, I use the right-hand rule also. Lastly, I have to label all of the link lengths. Now, let's start by finding the displacement from frame 0 to frame 1. The displacement between frame 0 and frame 1 is this vector right here. Remember that when I write that vector, I have to write it so that what I write will be true no matter what the value is for the joint variable theta 1. Right now, it looks like the displacement from frame 0 to frame 1 is equal to A1 in the z direction and A2 in the x direction. But consider what will happen when theta 1 is not 0. When theta 1 is not 0, frame 1 will rotate and move to a new location in the xy plane. To help you see this, let's imagine that we're looking down at this manipulator from the top view. I'm going to draw what this manipulator would look like from the top. From the top, we would see a circle showing the first joint, and we would see the x-axis coming off to the right, and we would see the y-axis pointing up. I'll scroll up a little bit so you can see what this joint looked like from the angled view. Now, when theta 1 is equal to 0, we will see the link A2 coming off directly along the x direction, leading to this second joint over here. But what will happen when theta 1 is, let's say, 45 degrees? In that case, we would see joint 2 having moved up to about here, and the link A2 would be seen like this. In this case, the displacement from frame 0 to frame 1 is no longer entirely in the x direction, but instead it has an x component and a y component, and we can see that from this triangle right here. This angle of the triangle is the rotation of the angle theta 1. And this distance right here is the same as this link length A2. From this, we can get the x and y displacements using the sine and the cosine. So let's write the displacement from frame 0 to frame 1. The x direction displacement is equal to the link length A2 times the cosine of the angle theta 1. The y displacement is equal to the link length A2 times the sine of theta 1. Now here, the z displacement, remember, is not 0. The z displacement can be seen from our original view. The z displacement between frame 0 and frame 1 is a distance of the link length A1. And here we're finished with the displacement vector from frame 0 to frame 1. I'm going to set this value aside while we find the displacement from frame 1 to frame 2. The displacement from frame 1 to frame 2 can be seen right here. Once again, right now it looks like this displacement is entirely in the x1 direction. But we can see that that will not be true as soon as theta 2 is no longer 0. In fact, the way that the displacement will change as theta 2 becomes non-zero will be the same for these two frames as it was for the 0 and 1 frame. The displacement from frame 1 to frame 2 will also have sines and cosines in the x and y positions. The x displacement from frame 1 to frame 2 will be equal to the link length A3, which is the hypotenuse in this case, times the cosine of theta 2. Similarly, the y displacement will be the length A3 times the sine of theta 2. Here, we have no displacement between frame 1 and frame 2 in the z direction, and this will be true no matter what the value of theta 2 is, so we can fill in a 0 for the z component of the displacement. Now we're done with the displacement from frame 1 to frame 2. Let's set this aside while we find the displacement from frame 2 to frame 3. The displacement from frame 2 to frame 3 can be seen right here. This appears to be a displacement entirely in the z2 direction. Will that be true even when d3 becomes non-zero? We can see that that will continue to be true no matter what the value of d3 is. Right now, the displacement from frame 2 to frame 3 is equal to the link length A4 in the z direction. But this distance is going to increase as d3 becomes large and this prismatic joint extends. So we can write the displacement between frames 2 and 3 like this. The displacement in the x and y directions are both 0, because no matter what value we have for d3, there will never be any displacement between these 2 points in x or in y. The displacement in the z direction will be equal to a4, the distance between these 2 frames when d3 is 0, plus however much this prismatic joint has extended. And this gives us the complete displacement from frame 2 to frame 3.